Thank you for your recording. That's fine. That's not. Yep, that's definitely the. Yeah, because we're in music theory. Then this new. That's hard. So that's like. Are you saying? Like, we're like transfer races. Oh, those are. Yeah. Breathing with that. We'll see. They're going to try to find me. But spring 2026 is the next one. Yeah, it's right 2 years short. I can do it. So. Oh, yeah. No, like all the thought. So, definitely people, I, yeah, you're really under research. And and for the nearly two, do we have that like long sheet with all the like constants like K's? Because like on the homework we had like this like 20-page thing with like a bunch of bond energies.
Yeah. So in the midterms, I think they'll give you a inside the question.
Okay. That's what I don't think people will. It's so hard to like go to that's what that serious
Okay, so any questions before we get started? So on the board is actually the summary of the chapter 13 and 14. We don't have too many equations to memorize for midterm 2, right? The things that's difficult for students is that it's hard for you to see what kind of solution that you have. Okay, so that's the things you actually practice the most. Okay, and I guess everybody in student actually know how to prepare your midterm 2 already, right? We focus on the things that you need to focus on. We watch the video, make sure you actually understand where I think about the questions. Okay, so that's actually the easiest way for you to actually get the correct answer in the limited amount of time. Okay, so I will just go through these things so that everybody is actually on the same page, because today what we're going to do is to finish the questions for chapter 14. Okay, and on Thursday's lecture, we're going to finish chapter 15 in one single lecture. Okay, and you should be able to see that the things that we spend most of the time is chapter 14, right? So that will be actually the main part of your return too. Okay. First first, by now you should be very familiar with the equations that we need to use to calculate the pH, right? So here I pretty much list the definition of pH, pOH, and how pH and pOH will give you in an aqueous solution, right? Your pH plus your pOH is always equal to 14. And you should also know that the little p represents the little log of certain value, right? So pK is actually the log of Ka. pKb is the log of Kb. Okay. And K and Kb inside the aqueous solution, when the product of these two will give a constant equal 10 to the negative 14. Okay. So those are the fundamental things that if you know what P means, then you should be able to figure out all the things, right? Then we've gone down to these 5 different solutions. For acid, you have strong acid, weak acid. Base, you have strong base, weak base, right? And then we have another solution called buffer. And the way you calculate the proton concentration for the acid, for the strong acid, it will be 100% dissociation of your strong acid. Therefore, the proton concentration is going to equals to your strong acid concentration. Okay. For weak acid, we're also referring to the acid with Ka smaller than 10 to the negative 4. Therefore, the proton concentration can be calculated using the square root of weak acid concentration times your Ka. Okay. Similarly, okay, base, you have exactly the same situation, but you substitute the H plus with OH minus, right? And acid with base, Ka with Kb. Then this is actually how you calculate the OH minus concentration. Then you calculate your pOH. Then you calculate your pH. Okay. For the buffer, there's only one equation to memorize, right? The HH equation, pH equal to pKa, negative log, conjugate acid over conjugate base concentration, right? So that's actually how you calculate the pH of different solutions. Okay. So by now you have no problem to memorizing all these equations, okay? Because that's not the difficult part. Difficult part is actually chapter 14, right? So when we talk about this titration, then on previous lecture, we spent our time to tell you when we do titrations, there are always 4 different zones. Zone number 1 is actually you don't add in any titrant. Okay, so depending on what the original analyte you have, then you have specific solution. Okay, then you start adding titrant, then things start to change a little bit, right? So you should know that the titrant can only be strong acid or strong base. Okay, so we always start from the simplest case, right? So this actually the first example we gave you, right? So if we start with a strong acid, okay, then you know at zone 1, you will have a strong acid solution, right? Zone 2 is actually you add in your titrant, in this case, strong base, into your analyte. Because right now you have a bunch of strong acid inside your glass. You add in a little bit of strong base. All of strong base will be consumed. Okay, so you still have a bunch of strong acid inside your solution. Okay, so in zone 2, you still have a strong acid solution. Yeah. When we hit the zone 3, which is actually an equivalence point, right? So at this point, the mole of your titrant and mole of your analyte will be the same. Okay, so under this case, you have the same amount of strong acid and strong base. So the net result is actually all these OH minus and H plus, they consume each other completely. Therefore, all you have is just water solution. Therefore, you end up with a neutral situation. Okay. And after you passing that equivalence point, meaning that right now you have more titrant than your analyte, meaning you have more strong base than strong acid. Therefore, you end up with a strong base solution. Okay. So this is actually what it means, right? And but those are the 4 zones are the things that you should know. The reason is because you should know what kind of solution that you have in different zone. Then you can actually use the previous equation to calculate the pH. Okay, so knowing the zone, knowing what solution is critically important. Okay. So for the strong acid, strong base, okay, I guess the situation is simpler. Okay. But when you have a weak acid to start with, okay, and for 4 different zones, you actually have different types of solution. Okay. So zone number 1, without adding any titrant, without adding any strong base, all you have is a weak acid, right? So you have a weak acid solution. Okay. But once you start adding in your strong base, okay, before you reach in the equivalence point, this is your zone 2, right? And then once you do that, every time you add in a strong base, it's going to consume one of your weak acid. At the same time, produce its conjugated base. So at this moment, you're going to have good amount of conjugated acid and base coexist inside your solution. Therefore, you're going to have a buffer. Okay, so once you have a buffer, you can actually calculate the concentration of your weak acid and its conjugated base. Then you calculate your pH, use HH equation. Okay, so you should know that in zone 2 is actually the buffer zone. Okay. Zone 3, again, all these acid base will consume each other, right? So when the weak acid got consumed, it produces conjugated base. Therefore, at the equivalence point, you end up with a weak base solution. Okay, therefore, if you calculate the OH minus concentration equals root of weak base concentration times Kb. Okay, and start from there, calculate your pOH, then your pH. Okay. And then after your equivalence point, you add in more titrant, then you have more strong base inside the solution. All you do is actually calculate your strong base concentration. Then you can actually calculate the pOH, then the pH. Okay. So this is actually when your titrant is a strong base, those are the situations you are going to have, right? You're going to flip the coin, okay, change your base into acid. Okay. Then it's basically the same thing. You just went through that logic again. Okay. So the things I want to point out is that For your weak acid, weak base, zone 2 is always buffered, always. Okay. So, and this actually probably students have most difficulty to figure out the pH. Okay, so we're going to go to a few examples. Okay. So to handle all these things, the equation that we always need to use is this. Every time you see this standard titration question, the first step is always figure out what is your VEP. For the volume titrant, you will need to add in so that the same amount of titrant and analyte. And when we say the same amount, meaning the same moles of titrant and analyte. Okay, so to calculate that, you use the concentration of your titrant multiply the volume of titrant. Okay, and we know that volume will actually at the equivalence point, so we call it VEP instead of calling VT. Okay, and it should equals to the concentration for analyte times the volume of analyte. The concentration we're going to use in chapter 14 is always the molarity, meaning it's actually moles per liter, right? So we times the volume that you end up with moles. Okay, so that's why you use this equation. And this equation is actually the equation we'll always use when we do the titration problem. There will always be your step number 1. Because once you know your VEP, and then compare the volume of titrant got into a solution, that was actually written in your question, then you will know it's actually either zone 2, zone 3, or zone 4. Okay, and once you know which zone you are, then what kind of solution you are going to have will be very clear. Okay? All right, so when we do this recalculation of the solution, okay, of your weak acid concentration or strong acid, strong base, weak base concentration, okay, we typically write some equation to help the thinking what's really going on. Okay, so here I want you to get used to this. This is kind of the nomenclature we're going to use. Okay, we are going to use H plus to represent strong acid, OH minus to represent strong base. Okay, for the weak acid, we use HA. Weak base, we use A minus. Okay, so the reason we use this one is so that you can just see it better. They're actually conjugated acid and base pairs. Okay, so you need to actually get used to all these expressions. Okay, so with that being said, this equation is the equation you will use. Okay, when you start with a strong acid as your analyte, okay, you titrate it with a strong base. Okay, so when you read that, that's the equation you have to translate. Okay, so this equation represents a strong acid is titrated by a strong base. Okay, if you know this exercise you have inside your question, you write out this equation, H plus OH minus, that give you H2O. Okay, and then similarly, this will be what? A weak acid is titrated by a strong base. It's going to produce your A minus. Okay, maybe I should still add this. Okay, plus H2O. Okay, so what is really happening is actually this guy get the H plus from your weak acid to produce H2O, and at the same time generate your A minus. Okay, so you want to actually translate the language into equation so that it helps you thinking. All right? Everybody fine with the things I just said? Okay, now we want to practice this again. This means you have a strong base titrated by a strong acid. that's going to end up with H2O. Okay. And then this will be a weak base titrated by a strong acid that's going to produce its conjugated acid. Is that clear? Okay, we're going to use these terms throughout today's lecture. Okay, we're going to use this equation to do all the calculations. Okay. And then one of the things that's very important, you should know that every time we do titrations, it is a hunger game. Okay, so it means whoever survives, it will be actually the dictators for the pH. Okay, for example, if today I titrate my strong acid H plus with my OH minus strong base, okay, let's say I have 1 H plus, 3 OH minus. Okay, they are going to kill each other, right? Who is going to survive? OH minus is going to survive. Therefore, OH minus will actually dictate the property of your solution. Since OH minus is a strong base, therefore you have a strong base solution. Is that clear? Everybody follow this logic? Okay, another example. Today, I have a weak acid, HA, is titrated by a strong base, OH minus. Okay, once I do that, I produce H2O plus A minus, right? So let's say I have 5 weak acid. I have 1 OH minus. Who will be the survivor? Who will be the survivor? Let me write out so you can see this more clearly. Okay, HA, weak acid is titrated by a strong base. Then we know the equation we want to write is actually H2O plus A minus, right? But H2O doesn't really matter because it's neutral. Okay. So right now I have 5 HA. I have 1 OH minus. Okay. And they're going to kill each other, right? Okay. Regardless if it's strong or weak, it doesn't really matter. They're going to consume each other equally. Okay, it means actually 1 HA is going to kill 1 OH minus. 1 OH minus is going to kill 1 HA. It doesn't matter if it's actually strong or weak, they're just going to actually form the water at the end. Okay. So in this case, you know, since your OH minus is actually a limiting amount, right? So you will be fully killed. But at the same time, that's what's going to happen, right? So we end up with 4 HA, 0 OH minus, 1 H2O, and 1 A minus. Okay? So now, who are the survivors? HA and A minus. So right now you have a conjugated acid base for this inside the solution, right? And this is only possible when you have a weak acid or weak base. Okay, so the what kind of solution do you have? Our first solution, what equation you should use? HH equation, right? So if you know the pKa of the conjugated acid, okay, and here you will actually get to know the ratio between your acid over conjugated base, right? So pKa minus log of that ratio will give you the pH of the solution. Is that clear? Everybody follow these things? It's very important. If you see this, then you will realize all the calculation is repeating the same process. Okay, so I want to make sure that everybody is actually understanding what I'm talking about right now before I actually really plug in all the numbers. Okay, I hope the logic is actually very clear to you now. Okay, And then this again will happen in all titration processes. Okay, so you just actually write out the equation that tells you. Okay, and then start to put in the numbers, see, okay, who's going to kill each other, who will survive. Okay, whoever survives, we calculate the survivor concentration. Know what kind of solution that you have, and use the equation in chapter 13 that you get your answer. Okay, let is actually the proper logic that you should have to calculate your pH quickly and correctly. All right, so any questions for the things I say? Okay, so we are playing a Hunger Game for chapter 14. You need to know that. Okay, very important. Hunger Game, survivor matters. Survivor will be the dictator in the end. Okay. All right, so in the previous lectures, I should finish this one, but I did not. I failed to finish this one. So we talk about buffer. And so we have to make sure we know what Ka to use. Okay. So if we read these questions, it says a buffer consists of 0.45 m KHCO3 and 0.42 m K2CO3. Given the K value for H2CO3 are Ka1 equals to a number, Ka2 equals to another. Calculate the pH of the buffer. Okay, so the keyword is actually very clear, right? Buffer. It is a buffer. So you know the equation you use has to be HH equation, right? So Q again is your pH of your buffer, right? Data, you have 0.49 N KHCO3, 0.42 N K2CO3, and then Ka1 for your H2CO3 equals to 4.5 times 10 to the negative 7. Ka2 equals to 4.7 times 10 to the negative 11. So that's all the data you have. Okay. So how to handle this? The first thing is actually you need to know what is the conjugated acid base pair that you have inside your buffer. Okay. So how do you actually figure that out? So you want to actually look at the substance that you have. Okay. So every time you see a compound, a formula that contains 1A elements, for example, sodium, potassium, lithium. Okay. The things that you should do is that throw it away. Okay. You know that that's going to carry positive 1 charge, right? And then write out all the other remaining things. Right? So first break it apart so you can see what is actually things that matters, because you know that potassium doesn't influence your pH at all. Okay? Therefore, you know the first substance, the things that matters is this guy, right? HCO3 minus. Okay? How about this? You have 2 potassium, right? So all these subsequent represent how many lead atoms existing inside the formula, right? Therefore, you know these 2 will actually dissociate. Okay? Then all the things that remain will be CO3, 2 minus. Anybody have a problem with writing all these things? I hope you actually know how to do this, okay? If you don't, like sometimes me, we can actually explain. It's actually very simple. Okay? So now, I hope you can see the species that we have is HCO3. minus and CO3 2 minus. How do you see? What are these two? Yeah, they are conjugated acid and base pair, right? So what's a K? K will be what? HCO3 minus becoming H plus CO3 2 minus, right? And that's a K that you need to use. Okay. So now you see in the question it gives you 2K, right? Ka1 and Ka2 for what? For H2CO3. Okay, so what does Ka1, Ka2 means? Ka1 means you start from H2CO3. You give out one proton and now with HCO3 minus. That's your Ka1, right? Means the first proton dissociation. Okay. This guy can do it again. And this, we call it Ka2. All right. So if you look at these two equations, which one actually agrees with the one we're actually looking for? It's actually the second one, right? Therefore, the K you should use is Ka2. It's the one that you should use. Okay, because for the buffer, we know the pH equals to pKa negative log conjugated acid over base, right? So the things that you need to decide is actually what K that you want to use. Okay, the K you need to use has the K that ties your conjugated acid and base together inside a single equation. Okay, so it's actually the second equation that can tie these two species together. Therefore, the Ka you should use in this case will be Ka2, not Ka1. Okay? Therefore, you know you should use negative log 4.7 times 10 to the negative 11 minus log. Who is your conjugated base? The conjugated acid, HCO3 minus, right? Therefore, the concentration you should put is 0.49 on the top. Base will be 0.42 at the bottom. Okay. So once you do these things, then you will be able to calculate the pH. The first thing is 10.33. Second thing is 0.067. Therefore, you know the pH of this buffer is going to equals to 10.26. Okay, that's how you solve this problem. Any questions? Okay, I hope this is clear. Okay, so let's recap the things we went through. Okay, so when you read the question, things you know that okay, apparently it's actually a buffer. Okay, the density charge here is actually you have two Ka. One's Ka1, one's Ka2, right? Which one you should use? Okay, you don't know which one that you should use. You should know what is your conjugated acid and base pair. Okay, so you go back and analyze the conjugated acid base pair you have is HCO3 minus and CO3 2 minus, which represent the second dissociation of your H2CO3, right? Therefore, you know your Ka has to be Ka2. Okay? And I just plug in the HH equation and get a pH. Any question for this? Yes. So do you have a problem with the equation I wrote there? H2CO3 become H plus, that give you HCO3 minus. Oh, you have to find, you can use the equation that contains the conjugated acid and base pairs. It's a single equation. So if you look at the first equation, Ka1 equation, you have H2CO3 and HCO3 minus. Right? If you want to use Ka1, that means the conjugated acid base pair has to be H2CO3 and HCO3 minus. So that's not what you have here, right? What you have here is actually HCO3 minus and CO3 2 minus, which is both show up in your second equation. Therefore, you know the second equation is actually the equation that you need to use. Therefore, the Ka2 is the Ka you should use to plug into your HH equation. Does that make sense? Does understand this? Okay, cool. Any other questions though? It's very important you see what conjugated acid base pair you have, so you can really decide which Ka to use. All right? So this is actually one of the trickier questions for the buffer. Okay, but I hope everybody can understand it now. Okay, I want to actually go to this standard titration question first. Okay, we'll do the question first, and then we go back to question number 3. Okay, so if you read this question, it says, determine the pH at equivalence point in this titration. Okay, in the Kb of this species is 1.6 times 10 to the negative 6. Okay. What's the keyword here? Good, equivalence point and titration, right? So this is actually a very standard titration problem. Okay. And then you want to calculate the pH of this solution, right? So once you go through titration problem, then you actually know which zone you are. Therefore, you know what kind of solution that you have. Therefore, you can calculate pH, right? So that's actually the largest flow rate you actually have. Okay, let's look at data that we have. So we know we have 0.116 m morphine. Okay, and then you have 30.77 milliliters, right? Apparently, this is actually your analyte, right? Your titrant is what? 0.231 m HCl. Okay. So this is actually the setup that you have, right? And then you also know the Kb of morphine or your analyte equals to 1.6 times 10 to the negative 6. Okay, so this is all the data that you have, right? And then the first thing you do is actually get back to the simple system that we have. Okay, using A minus to represent your weak base, HA for your weak acid. Okay. So with all this, first thing, ask yourself, what's your analyte? What is your analyte? Strong acid, strong base, weak acid, base, or buffer? Weak base. How do you know it's weak base? So a few clues, right? Do you see this? If you Kb, right? If you give me Kb, it has to be weak. B means actually base, right? So a weak base, right? Therefore, you know the equation you want to write as what? Hydrogen with a strong acid. That gives you HA, right? Everybody fine with this? Okay. I want to make sure that you can write these things when you go to CASA. Okay, by yourself. All right. Once you have this, then if you read this question very carefully, you know you want to calculate pH at equivalence point, right? At equivalence point. Okay. So meaning you are going to have the same amount of A minus and H plus, right? Equivalence point means actually you have the same amount of titrant aniline. Okay. So that means actually you have a certain amount of this, certain amount of that. Okay, and this time most of your aniline, most of your titrant. At equivalence point, these two numbers they are equal, they are the same, right? So what's going to happen is actually these two is going to kill each other, right? So you minus Na, you minus Na, you're going to plus that much, right? Therefore, you know who is going to survive. The only thing that survives is what? HA. Therefore, you know at equivalence point, you're going to have a weak acid solution. Does that make sense? Does everybody follow the things I just said? Or you guys still feel confused? This is critically important. Critically. If you cannot do this, you're not going to solve it properly. Okay. Everybody follow this? I need some response. Okay. So once you have left things in mind, then the things you do is actually quite simple. Okay. First, how to calculate more of your aniline. Yes, the molarity times your volume, which is 0.116 times 30.77. Right? So you know that's how many moles that you're going to have. Yes, you're going to get millimoles, which this one will give you a millimole of 3.57 millimoles. Right? So you know you have that millimole. Okay. So more of your protons of your strong acid is exactly the same, right? So even you don't do calculation, you know it has to be 3.57 millimoles. Okay. Okay. And these two is going to consume each other, right? If you know, you're going to minus 3.57 minus 3.57 plus 3.57. So you end up with so the mole of your HA is equal to 3.57 millimole. Okay, so that's not what you want. What do you want? Okay. What you want is actually you want to know the concentration, not moles, but concentration, right? How do you know the concentration? The concentration of your HA will be computed as the mole of HA over total volume now, right? So the total volume can be calculated by the sum of volume of your titrant and volume of your aniline. Okay. Do we know the volume of your aniline? We do, right? How about the volume of your titrant? We don't know yet. But we can always compute the volume of your titrant using this concentration of your titrant times VEP equals the concentration of your analyte times the volume of your analyte. Okay, so the concentration of your analyte is 0.116, volume is 30.77. Concentration of your titrant is 0.231. Therefore, you know that's the volume of your titrant at equivalence point, right? Therefore, you know your VEP will simply equals to 0.116 times 30.77 divided by 0.231, which equals to 46.22 milliliters. Okay. So once you know this, you can know that the total volume at equivalence point will be 46.22 plus 30.77. That's going to give you a value of this one. Once you do this, VEP is 15. My bad, it's actually 15.45. So 15.45 plus 30.77, they give you 46.22. Okay, so this will be the total volume of your solution at equivalence point. Therefore, you know the weak acid concentration can be computed as 3.57 millimole divided by 46.22. And then this will give you a number of 0.0772. So you have a weak acid with this value. Okay. Then you can calculate the proton concentration of a weak acid. It's going to equal the square root of weak acid concentration times your Ka, which will be 0.0772. Do you have Ka here? Do you have Ka here? You don't, right? You only have Kb, right? Therefore, you have to actually recalculate your Ka by using 10 to the negative 14 divided by your Kb, 1.6 times 10 to the negative 6. Right? So your Ka was calculated from your Kw over your Kb, which is what we have here. Okay? So once you do this, you can get your proton concentration equal to 2.2 times 10 to the negative 5. Okay, therefore your pH will equal to negative log 2.2 times 10 to the negative 5, which is going to equals to 4.66. Okay. Any question for the things we just went through? How do you think you can do these things yourself? You can see these things is pretty lengthy, right? That's why most students got cooked. Right? Because anything you make mistake along the way, you're not going to get the correct answer. Okay? So do you see why I emphasize so much I have to break this down, right? In the beginning, in chapter 13, we keep emphasizing know your solution. So you know the equations, right? If you see that the problem starting from here, do you see this very last section? This is actually the things we train ourselves a lot in chapter 13. Right? I have a weak acid, right? I know my weak acid concentration, then I calculate pH. That's actually the standard question you have for chapter 13. Right? So that's why I want you to really memorize those things, because once you know that you just plug in the very last part, it becomes not a problem anymore. Okay? So this we can actually get familiar and become experts that can we actually analyze what kind of solution that we have, right? So here we practice how to write the correct chemical equation to help us think. Right? You know we start from weak base, that's why we write this A minus. You know we have titrate with a strong acid, that's why we write this H plus. Okay, and you know once these two deal with each other, you're going to produce HA, right? So let's actually the things that have to realize that the species you're going to have inside your solution can either be A minus, H plus, HA, or a mixture of A minus and HA. Okay, because different combinations give you different kind of solutions. And the equivalence point, we know you percent amount of A minus and H plus, meaning that they're just going to cancel each other and then you don't see that anymore. Therefore, you'll see that the only thing remains is actually your HA, right? So before you actually do any calculation, you should have in mind that I'm going to have a weak acid solution, right? That's the things you need to practice to help yourself to see. Because you know, I'm going to have a weak acid solution, then you know the very last part already. That's the things you need to do, right? And all the other things we say is actually just to figure out what's going to remain, recalculate the concentration of the remaining species. Okay, so by doing that, the benefit is that you can't master these two parts separately. Okay, in order to make sure you are really good at both parts. Okay, if you can do this, then you'll realize the things we do is exactly the same over time. Okay, so this is actually how you do these questions. All right, so any question for this? Yes. You can. So just make sure you are consistent. If you want to use liter throughout, then use liter throughout. If you want to use milliliters, let's use milliliters throughout. Okay. Any other questions? Okay, so let's read the questions again. Okay, this is actually very important. So the sentence I want to pay attention is that in titration of this species with the other species, the structure will be like A, titrate A with B. A will be your analyte. B will be your titrant. Okay, so based on the description, you should be able to see that and tell who is who. Right. The other thing is that you should know that for your titrant, it can only be strong acid or strong base. Right. Inside the question, at the very end, it gives you the KB of morphine. Telling you that morphine cannot be your titrant. Right. Since it cannot be the titrant, it can only be the analyte. Okay, so there are multiple things you can actually see to figure out who is actually your titrant, who is actually your analyte. All right. So let's how you do question number 4. Get back to this. Okay. Determine the volume in milliliters in 0.55 m HBr needed to reach half equivalence point in titration of 4430 certain volume of amine. The Kb of the ammonia is a certain value. Okay. Again, the keyword is, this is the keyword, right? Titration is the keyword. Okay. So you know it's chapter 14 type of questions, right? And the things you want to find is what? The volume half equivalence point, right? Means actually you need to figure out what is actual equivalence point, the volume of your equivalence point divided by 2, then that's your answer. Okay? Data. You have 44.37 milliliters, 0.703 m NH3. AB for your NH3 equals to 1.8 times 10 to the negative 5. And then the other one is 0.551 m HBr. Okay? So that's all the data that you have, right? So again, when you see this, you want to know who's your titrant, who's your analyte, right? Who's your titrant? How do you know it's HBr? It's a strong acid, right? The other one is actually weak, right? You have the Kb, right? Therefore, you know this is actually your analyte. That's your titrant. Okay? So your titrant is a strong acid, right? One of the seven strong acid, right? Therefore, you know it's H plus, right? The other one is actually weak base. Therefore, we write this. You know that is actually the equation that you want to have to help you to think. Okay. Then it tells you this is actually the concentration and volume of your analyte. This is the concentration of your titrant, right? And it asks you about the half equivalence point. So it's actually very simple, right? All you need to do is actually using the concentration of your titrant times your VEP is going to equal the concentration of your analyte times your volume of the analyte. Okay, then you can figure out your VEP divided by half, then you got your answer, right? So concentration of titrant is 0.551. VEP unknown. Concentration of analyte 0.703. Volume 44.37. Therefore, you know your VEP is going to equals to 0.703 times 44.37 divided by 0.551. Then you're going to get a value of 56.4 milliliters. Okay, but this is actually not question 1, right? You want to have the half equivalence point. So half equivalence point will equals to 56.4 divided by 2, which is going to give you a volume of 28.2 milliliters. Right, that will be the answer. Okay, very straightforward. Okay, any questions for this? It shouldn't, right? It should be actually straightforward for you. Okay, but let's move to another things I want you to stop. If I ask you, can you calculate the pH of the solution? That's the thing that's actually more challenging, right? So how do you calculate the pH of this solution? So again, you need to start to analyze the mole of your titrant and analyte, right? And figure out who are the survivors. Okay, so the mole of your analyte will be 0.703 times 44. So this point, the mole of your analyte, 0.703 times 44.37, right? What's this value? Anyone? Calculator, please. I did not calculate this value myself. I have the end result, but I don't have this number. 31.1 millimole, right? How about your strong acid? It should be 15.55 millimole, right? Because it's actually half equivalence point, meaning you add in half amount compared to your analyte. Okay, so therefore you know this is actually a situation you have to start with, right? And they're going to cancel each other. Okay. Apparently H plus will be fully constant, right? So you need to minus 15.55 minus 15.55 plus 15.55. Therefore, you end up with right. So what kind of solution do you have? It's a buffer solution, right? Because you have your HA, you have your A minus. Therefore, you know you have a buffer solution. Okay, so then you also calculate your pH, right? pH equals to pKa, negative log, conjugated acid over the conjugated base. Okay, so do you have Ka? If you go back and check, again, you don't have Ka, right? So again, you calculate your Ka. So you know the first term will be negative log. Your Ka can be calculated by 10 to the negative 14 divided by your Kb, 1.8 times 10 to the negative 5. Right, that will be your first term. Okay. Second term, negative log. What's your acid concentration? Well, the mole of your conjugated acid in this case is 15.55 divided by the total volume, which will be 28.2 plus, okay, so 44.37 plus 28.2. Right, so there will be your acid, conjugated acid concentration. For your conjugated base, it's actually exactly the same. Okay, therefore you know this, your numerator and denominator, this guy and the bottom guy, they are exactly the same. Okay, therefore you have log 1. Log 1 is going to give you a value of 0, right? Therefore your pH is simply your pKa. Anyone can calculate this number for me? 9.25. Okay. So again, this is the weak base actually with a strong acid at half equivalence point. Okay. So at half equivalence point is actually a very interesting spot. Okay, because half of your weak base will not become its conjugated acid. Okay, so your second term, negative log with acid, the conjugate acid over base, that term will equal to 0. Okay, so pH is going to equal to pKa. Okay, again, we're actually repeating this pattern now. Okay, so you can see every time I have my data list out, I try to write out the relevant equation to help myself think. Okay, so I just compute the VEP, right? So you can always compute your VEP because it helps you understand which node you are at. Okay, and then you compute once your acid and base actually interact. Okay, who will be the survivor? Okay. Based on the survivors, you can predict what kind of solution that you have. Right? In this case, it's actually zone 2. Because half equivalence method before your equivalence point, right? It's zone 2, right? So in our very beginning of the lecture, right, it is actually a weak acid or weak base actually with a strong acid. Zone 2 is always above the zone, right? And this has demonstrated that why this is a property, because they put amount of conjugated acid and base coexist inside your solution. Okay, and plug into the differential equations. That's how you calculate the final pH for the whole solution. Okay, any questions? So this is actually one of the most challenging questions you're going to see. Okay. Okay, so now look at this. A buffer contains 0.1 N of an acid HA and 0.27 N of conjugated base A minus. Has a pH of 4.83. But the pH after you add in 0.021 mole of NaOH. Okay, let's say the overall solution in the beginning is 0.79. Okay, a very, very lengthy description. Okay, this is probably actually the most complicated question you're going to see in this chapter. Okay, this question is very specific questions. It's pretty much the most complicated one you're going to see for chapter 14. Meaning that if you can actually feel very comfortable solving this, you should be good for all other type question problems now. Okay. So first thing first, what are the keywords? Okay. Buffer definitely is actually one of the keyword, right? Every time you see buffer, what do? Write on your HH equation, right? So every time you see this word buffer, don't have a second thought, just write down the HH equation, starting from there. Okay. All right, so eventually, what do you want to have? You still want to calculate pH of the final solution, right? And then what do you have here? In the beginning, you have your buffer. That means actually you must have your HA, you must have your A minus, right? And then for your HA, you have 0.15 N. For your conjugated base is 0.27 N, right? And then it tells you, okay, so into this solution, overall you have, so the volume total of your buffer, okay, the volume of your buffer equals to 0.79 liter, right? And then you have a pH equals to 4.83. Okay, and then you want to know the pH after adding 0.021 mole of NaOH is a strong base, right? Therefore, you know. I will just write out OH minus. Okay. So that's all the information that you get so far, right? Okay, so think about this. The question is actually trying to figure out the pH of a buffer after adding in your strong base, right? So what would the strong base interact with your buffer, right? Your buffer, inside your buffer, you only have weak acid with base. Yeah, and you get in your strong base. Therefore, you will only interact with your weak acid. Okay, so that is actually the things that you have. Okay, so this is actually going to be similar to the things we described. You titrate a weak acid solution with strong base. Okay, so therefore, you know, the equation that can help us think is that HA plus OH minus, that's going to give you H2O plus A minus. Right, that's the equation that you use. Right? So you want to calculate after this has happened, right? Who are the survivors? Okay, so first you need to know how many more do I have for my HA? It will be the concentration of your HA times the total volume, right? Which will be 0.15 times 0.79. A minus 0.27 times 0.79. Right? That's how many moles that you have. Okay, so if you do that calculation, this gives you 0.1185. This gives you 0.2133 moles. Okay? And then inside this question, it says, I add in how many more of strong base? That much, right? Therefore, I know here I have 0.021. Okay, so apparently this and that, they are going to cancel each other, right? Since your OH minus is smaller amount, therefore you know it will be fully consumed. Therefore, you end up with 0.0975 mole of your HA. You don't have OH minus. You do have 0.2343 A minus. Right, so this is actually after interaction. Right? So what do you have? Who are the survivors? Weak acid HA and A minus. Right? So again, you still have a buffer solution. Okay. So you want to know the pH of these solutions, right? Therefore, you can calculate pH equals to pKa negative log 0.0795. Okay. Total volume is 0.79 divided by 0.2343, 0.79. Okay. This term, of course, you can calculate it, right? So just plug in numbers into your calculator, then you are fine. But do you have your pKa? You don't have pKa, right? So this thing is missing. However, if you look at the question again, it tells you for the original buffer, you have a specific pH, right? And then you know the pH equals to pKa negative log. Your acid 0.15, your base 0.27. Right? So in the original setup inside your questions, even though it provides you the pH, what it's trying to tell you is actually your pKa, right? So your pKa will simply equals to 4.83 plus log to 7. Okay, so here you know your pKa is going to equals to 4.37. Okay, so once you get it, come back to here. 4.37 minus, what's this value? Negative something? Negative 57, I guess. 0.57. Therefore, you end up with the pH equals to 4.94. Okay. So this is actually how you solve these specific questions. Okay. So I want to recap these questions. Okay, this question is actually the most challenging questions. Okay, for chapter 14. Okay, because it is not like the titration question we described in the beginning, right? It starts with a proper solution, right? And it starts in some strong acid or strong base. Okay, in this question, it's actually in a strong base OH minus, right? Then you might know that your OH minus is going to consume your weak acid, producing more its conjugated base, right? And calculation-wise, okay, because always inside buffer setup, so the equation you use is always very simple. pH equal to pKa make the law of acid over base, right? So equation-wise, this is not difficult. Difficult part is actually, can you really know when the question say I ate certain amount of base, what does it do, right? Can you write out the equation? HA plus OH minus produce A minus, right? That is actually the key equation you can actually write out. So they can actually really figure out who will be the survivors at the end, right? Because it is actually at the end situation that tells you what kind of solution you're going to get. Okay, so that's the things that you need to practice a lot. Okay, so if you can really master this technique, then you should be fine for the written 2 actually, not just chapter 14, because you can see that chapter 14 contains a lot of things in chapter 13. Okay, so this will be the very last question we want to go through. The pH of 0.5 m acetic acid is 2.52. Calculate change in pH when this is adding to that. Okay. What's the question? What's the Q? Okay, good. They have pH, right? And then specifically, you know this can be calculated by the pH of your acetic acid is a weak acid, right? HA. Okay. Minus the pH of this and lead. Okay. You have two solutions here. The first one, apparently, it is a weak acid solution, right? How about the second one? What do you have? So read this carefully, right? Because these are actually the things that you can recognize what kind of solution that you have. Because once you know that, then it's done. You add in, what's this? It's a salt, right? Do you see that Na? Every time you see those elements, what do you do? Pull it apart from your chemical formula, right? So you minus Na plus. So what do you end up with? CH3COO minus. Can you see this? These are equivalent. You need to see this. Okay. So you throw in CH3COO minus into what? Into a CH3COOH solution. What are you going to have? Did you see this is actually your A minus? Did you see that's your HA? Do you see that? That's the things I want you to see. Okay, every time you see you throwing an A minus into a HA, what are you going to get? Buffer. A buffer solution is actually your second solution, right? Can you calculate pH of a buffer? Yes, HH equation. Okay, so once you know your buffer pH, you know your original acetic acid pH, you can calculate your delta pH. I hope the answer is yes, it should be straightforward, right? But what the difficulty here is that at least half of the students cannot see you have a buffer solution here. Okay, so I want you to see this, okay? So let's go through these things quickly, okay? Data you have, the pH of your HA equals to 2.52, right? And pH of your buffer is the things you want to calculate, okay? So your A minus is 1.59 gram. Add it into a HA solution, which is 0.5 M, 49.9 milliliters. Okay, so apparently you're going to have a buffer. Therefore, you know the pH equals to pKa negative log your conjugate acid over base concentration. Ka is actually given, so negative log 1.8 times 10 to the negative 5 minus log acid concentration is actually given. Base is not, so you to actually calculate it. Okay, so the way you calculate the concentration of your base is that mole of your base, right, which is 1.59 divided by the formula weight, 82.03, divided by the volume, it's 49.9 divided by 1,000, right? So once you do that, you're going to get a concentration equals to 0.0499. Okay, so this will be 0.0499. Therefore, you know the pH of your buffer is going to be equal to 0.3884. Oh, sorry, not 0.3884. This will give you a value of 4.6351. Okay, therefore the delta pH was simply 4.6351 minus 2.52. That absolute value equals to 2.12. And that will be the answer. Okay. So the bigger things for this question is that can you see what kind of solution that you have for the second one? Right? If you can, then calculate the pH. I think everybody can do it. Okay, so I'm really late today, but thanks, that's it for today. Thank you.